Right, I think we can start. And I would like to start by welcoming everyone today, and I hope you're having a great day today. I want to thank you all for joining us today in our session with JetBrains and Azul. Today, we'll be discussing how to boost JVM scalability and performance with Kotlin on the Azul runtime. And with that, I also want to celebrate this new collaboration between JetBrains and Azul. Cody and myself are loving this new collaboration between JetBrains and Azul, and I'm sure Jiri is too. So let me first introduce myself. I'm Simon, and I live in Antwerp, Belgium. I've been working with the JVM for over a decade, and I've also been working with Kotlin for over a decade now. I used to work as a principal engineer for the last 5 years, but now I'm working as a developer advocate for Kotlin at JetBrains. And for those that do not know Kotlin, Kotlin was a language that was originally built by JetBrains with a strong focus on performance and developer ergonomics and safety. But it's now being developed by the Kotlin Foundation, which is an open source foundation founded by JetBrains, Google, and Meta. So, Jiri, could you tell us something about yourself and what Azul offers to Kotlin users on the JVM?
Thank you, Simon, for the introduction. So let me maybe introduce myself first as well. My name is Jiří Holusha. I come from the Czech Republic, so that's why we have that special R letter that no foreigner can pronounce correctly. We just made up the letter to make ourselves feel special. I work at Azul as a product management director, and that's a scary title to be on a technical talk, but I can assure you that in my previous professional life, I was a quality engineer and I was a performance engineer in Red Hat and at Hazelcast before I joined the dark side of product management. And today I'm very happy to co-present with Simon and the JetBrains team, because we do, well, what do we do? I think that we'll get into it in a minute of, what does Azul do and how does it relate to JetBrains? So Simon, what do you think? Shall we get started?
Yes, I'm very excited to learn more about what Azul has to offer us.
All right. So how does Kotlin and the JVM, how do they work together? Or how does JetBrains and Azul work together? So this is probably obvious for the Kotlin developers, but it's always good to reiterate. Is the important part is that Kotlin is a JVM language, right? And as such, it runs on top of a JVM. So there's a Java runtime. So there's a Java runtime that interprets that it compiles the code to the machine code that then gets executed. And that's where the story kind of begins, where the joint collaboration begins, because JetBrains is responsible for Kotlin, the authors, right, the founders of Kotlin, and the biggest contributor, as far as I know. And Azul, that's just synonym for Java. We do Java runtimes, we do builds of OpenJDK, but we also do an enhanced Java runtime. That's called Azul Zinc JDK. It's part of our Azul Platform Prime product. That's a marketing name for the product. But since this is a technical developer focused talk, let's use the name of the JVM, Zinc JVM. And what is Zinc JVM actually, and how does it differ from OpenJDK? The whole point is that Zinc JDK makes your applications run faster. It's a standard Java, standard JDK on steroids, or on fire, as I tried to picture on this logo. Before we even get to the differences of Azul Zinc versus OpenJDK, the standard vanilla Java, quote unquote, why would we even want a faster JVM? Why would we even care? And where do we make business, right? So we typically, with our applications, in Java, in Kotlin, or in any other JVM language, or actually in any language, we care about performance for multiple reasons. First, we care about speed, right? We care about throughput. We care about how many transactions, how many operations can we handle, how high is the load that we can handle before our application service basically gives up given the resources. So that's a throughput in terms of performance testing or performance metrics. That's a throughput. We also care about customer experience, about the application responsiveness, how pleasant it is to use our application. And that's usually referred to as measuring latency, the time it takes for the operation to complete, right? But since you send it till the answer comes back, sometimes referred as a response time, sometimes they are used interchangeably. Some people are very particular about the differences between those, but I'm going to use that as a synonym: response time and latency. So that's how a faster JVM actually affects the performance of your application. That's an improved performance. But one of the less obvious ways how to utilize better performance is actually the cost aspect. If you have a application that runs on your hardware, and then the application runs faster, meaning that it's able to process more load using the same hardware, you can actually process the same load using less hardware, and that results in infrastructure cost reduction. So that would be the values, the business values that we propose of why would you even consider faster JVM. And the whole point of Azul Zinc JVM is that you have your application, you develop your application, you don't want to change it, you don't want to optimize the code, you don't want to do code changes, but you need it faster. And the idea is that if you switch the JVMs, it can heavily affect the performance of your application, hopefully for the better. We usually, at this point, get a question of like, so what's different about your JDK, right? How do you differ from what I'm using now? So Azul Zinc JDK is based on OpenJDK. OpenJDK being the standard vanilla Java. But we took some key parts of it out of it and re-implemented them to a better, more performant, different version, or added something to the VM. What are those pieces? In the JVM, we have the just-in-time compiler, the compiler that transfers the bytecode, the Kotlin created or Java created bytecode into a machine code. And the compiler does a lot of optimizations to make your code more performant. We took the usual hotspots C2 compiler, took it out of the JDK, and implemented a different one that we call Falcon, which is LLVM-based compiler, LLVM-based JIT compiler. And the net outcome of it is that our compiler produces smarter code, more efficient machine code that then runs faster. Another component that we re-implemented is the garbage collector. So the garbage collector in the JVM is responsible for, surprise, surprise, collecting garbage, meaning your unused memory, right? There are a lot of garbage collectors in the standard OpenJDK, Parallel GC, G1 GC, ZGC, Shenandoah. There are quite a few. We have our C4 pauseless garbage collector. The C4 stands for concurrently compacting. I always mix all the C4s up. But the point is, it's a concurrent collector. Sorry, continuously compacting concurrent collector. The idea behind this, it's a concurrent collector. So we basically eliminated the stop the world GC pauses that heavily affect latencies, and that enables us to have unlimited Java heap sizes. Pretty much, we have examples of running terabytes of heaps. The largest ones, I believe, are in production that we have are 6 terabyte heaps per JVM. We are the original authors of the concurrent garbage collector algorithm, and we have more than a decade of experience with those. Another component that we created is the Ready Now warm-up accelerator, and that's a feature of the JVM that enables you to shift the JIT compilations in a different time, even before it's actually needed. So when the application starts taking load, it actually is already done with the JIT compilations. So it doesn't interfere with your application resources, with the resources needed for your application. Therefore, you don't get this ugly behavior of interference between application and the JVM, usually referred to as warm-up period. Lastly, there are a lot of other things in the runtime that can get tweaked, that can get better. Over the years, we accumulated a lot of small, minor, subtle differences, reducing the smallest pauses in the JVM, context switch related, locks related, and I wouldn't be able to even name all of them. The net effect is that the whole JVM is especially focused on performance and consistent execution, removing any single outliers that would affect your performance and your latency. So we wanted to, we established a collaboration between JetBrains and Azul, and we wanted to see, we want to investigate how do we affect Kotlin performance. And that's where I would turn over to you, Simon, because you guys did all the benchmarking, you guys tried it out, and you wanted to see the effect of our JVM. So how did it go?
So tracking performance is always a very tricky thing to do. And we at JetBrains, we use a lot of Kotlin ourselves. Obviously, we also use a lot of Java. We build a lot of Java products as well. So we are looking at our own usages, but we also went looking in the community because there is a lot of well-known, well-established benchmarks already out there in the community that go way beyond Java and the JVM. For example, Tech Empower. And what is very interesting about these established benchmarks is that they compare things in a similar way and they give us more confidence because building benchmarks is very hard. There's also the Renaissance benchmark where Kotlin is currently not yet represented, but we're in the process of integrating Kotlin into the Renaissance benchmark. We also did some in-house benchmarking because we want to be able to see, how does Tech Empower compared to Renaissance and to our own, internal testing that we developed together with Azul. So let's take a look at the actual results to see how changing the JVM runtime can affect your Kotlin performance. And during our testing, we saw that there was a significant performance increase, not only in latency, but also in throughput, like Jiri just discussed. And we did 2 kind of in-house tests, which was CPU-based, and another one which was memory-based, so that we are targeting different kind of optimizations in Zing, like the GC, the concurrent garbage collector, GC just explained, and the other enhancements in the JIT compiler. And we can see that there is about a 25% improvement in latency, which means there is a reduction, a significant reduction in response times. And we can also see that our server was able to handle about 35% more throughput, right? So we see an increase in throughput. And what I think is very interesting about these benchmarks is that you can see that they are almost identical to the Java benchmarks that we saw previously from Azul with Zing. And that shows that these improvements benefit anyone on the JVM, right? So whether you're working with Kotlin or Scala, these JVM improvements, they can help any program. And I think it's really clear here that using the Zing runtime with Kotlin can really benefit your performance, your applications, and as GZ mentioned, reduce your infrastructure costs, which I think is really significant. And with that, Jiri, I would love to know if you could give us some more details on what is actually going on inside of the JVM, how some of these optimizations are working, how they benefit our programs.
Yeah, thanks, Simon. So that's the usual question that we get once we try our JVM. What the hell is going on, right? How did you do that? The answer is it depends, right? No, we're all we've all been in the business for a while. So I'm going to give you an examples of what our JVM does and how it actually affects performance, throughput, and latency, but in general performance. One of the first examples, as I said, is the garbage collection behavior. So the default garbage collector in OpenJDK is still to this day G1 garbage first GC garbage collector. This is a very good garbage collector, right? It's mostly concurrent, but not always, and it provides good behavior for usual applications. But it is not a low latency garbage collector, ultra low latency. This is a chart, and this is a chart taken from our tool that we call GC Log Analyzer. So that's why it looks, not so pretty as Simon's charts, because this is actually from the tooling. And what you can see here is the lengths of the stop the world GC pauses in milliseconds through the memory, one of the benchmarks. You can see that the values, that the pauses range in between, like, let's call it on average around like 8 milliseconds, going up above 10, 12. So how this is going to affect the latency of our application is that if you have requests constantly coming, and they arrive during the garbage collection pause, you will necessarily see the latency of those requests, at least the GC pause, plus how long it takes to process your operation. So that's a direct effect. That's a very known phenomenon in the JVM world, that stop the world GC pauses affect latencies. Let me show you an example of what the same chart, what the same benchmark looks like on Azul Zinc. At the first sight, when you look at the chart, you see, oh wow, this is spiky, right? The spikes are much higher. But let's take a look at the Y chart, the Y-axis, right? You can see that most of the pauses are actually sub-millisecond, so in microseconds, right? And the peak, the longest pause that we have touches less than 3 milliseconds in here. And if you remember the previous chart, it wouldn't go beyond like 6, 7 milliseconds. So that's a direct reduction in the latencies that you can observe with your application. And obviously, the larger the heap, the larger the live set, the more data you store, the larger the allocation rate, the better the difference will be. We have a lot of experience of getting through hundreds of millisecond pauses to sub-millisecond pauses, right? It's just the way that let's say, it's not a legacy garbage collector, but the older non-concurrent garbage collectors, that's an inherent effect. One very important thing that we didn't mention in the beginning of the talk is that if you have any questions, please feel free to send them over to the chat, as I saw happened in the pop-up, and we'll try to answer them in the end of the talk. Otherwise, I would absolutely lose track of my thoughts. So the GC is just one aspect of the JVM that makes the performance better. What is the other example, the major example? And at this point I need to talk about the JIT optimizations. So let's take this example of a code which adds arrays, only the even numbers together to in an array, right? This is actually example from a production code, right? By the way, but it may seem like an artificial example. In the JIT optimization world, it's quite hard to find a very nice demonstration of when two compilers do things. So that's why we picked this one, but it is coming from a real world example. So with this code example in mind, right, let's see the actual machine code, the assembly code that the OpenJDK's C2 compiler produced. Unfortunately, I don't have the time to explain, to teach you how to read assembly code. That's what we do at Azul, but we don't expect everybody to be able to do that. But I think the general sense you'll see in here. You'll see two same boxes. Basically, it's reading the value, then a condition, that's a test instruction. Then there is a conditional jump, JN, jump, right? Jump, so that's a condition, whether it adds it or not. And then there is the add instruction. So what does this assembly generated code does? The C2 for some reason decided to unroll the loop for two elements. So it's processing two elements one by one, but it has a test, it has a jump, so it has a branch, it has a conditional branch to another part of the instruction on the instruction list. Let's see what. So this is a scalar generated code, right? Let's see what we end up with Azul Zinc with the Falcon JIT compiler. And again, I think the picture repeats. The GC picture repeats. At the first sight, it looks absolutely scary. It's way more instructions, right? But let's take a look a little more what these instructions are. And reading this code is actually much more complicated. So let me simplify way more. The V instructions stand for vectorized. So all of these instructions are using the AVX2 vector capabilities of the hardware. This is generated on an Intel CPU, I believe, Skylake and later. So what the compiler decided to do is to actually load multiple values on the registers, then mask them all at once with one instruction, then do comparisons all at once with one instructions, and then add them together. What this code does, and why it's way more efficient than the OpenJDK one, way orders of magnitude more efficient, it's that it's more CPU and memory friendly. First of all, it does multiple elements per one iteration. Secondly, this code has no jumps. It has no branches. So the CPU can do all of its magic of prefetching CPU instructions. It cannot have branch misses. And that's an important, very expensive operation in the hardware CPU world. Also, you can see that the elements are being popped on the registers like sequentially. So you can prefetch multiple data, right? You can prefetch multiple data as preemptively without kind of jumping back and forth in branch misses and cache invalidations. And all of these little nuances makes this code much more hardware friendly, much more modern hardware friendly, which results in orders of magnitude better performance. And that's the difference of, these are the examples of our JVM, what it does differently, what it does better. Of course, just like with every application and every single performance test, the mileage may vary. For your application, it's different. For other applications, it's a different result. But these are the examples of how we do it better and how we enhance the performance of the applications and even the Kotlin applications that we just proven together with JetBrains. And I think that this shows promising results. This is a good start, and we are committed to continue working with JetBrains on the future collaboration. And Simon, what did you have in mind?
Well, I'm very excited for these collaborations because I think there is a lot of, space that we can work together to make JVM specific optimizations. Like I said in the beginning, JetBrains is not only very invested in Kotlin, but also very invested in Java, and it's very invested in the JVM platform in general. And I think we've also shown that, any JVM improvements, benefits anyone on the JVM regardless of language, which is again an amazing feat of the JVM. But there might be in the future, Kotlin specific optimizations that we could, discover and, work together with Azul to improve. One thing on my mind is, for example, coroutine specific optimizations. And in case you're not familiar with Kotlin coroutines is Kotlin's solution to performance and safe concurrency, with good developer economics and strong type safety. But these reactive machineries, they come with some implementations, and potentially these things can be optimized like GZ just showed us in Jet. And potentially there's more optimizations of common Kotlin patterns that we have not identified yet, that we might identify in the future, and our collaboration could help us make those improvements in the future. And with that said, I want to thank you, GZ, for the amazing explanation. I think for me, it was another great reminder of how powerful JVM is and these cheat optimizations are, that I do not have to think too much about optimizing my code myself, because you are doing that for me. And yeah, I want to thank everyone for joining us. I want to thank Azul for hosting me tonight. And yeah, I want to thank everyone for coming in. Let's answer some questions. I think we got a very interesting question from Ulrich, GZ.
All right, so let me read it out loud. So, does Azul provide a tool to automate the process of setting the JVM memory parameters, like heap size, and the container resource limits? Avoid OOM kill when the JVM tries to allocate more memory than allowed by the container resource limit. So, does it provide a tool to automate it? Let me try to see it from multiple angles. Like the first thing to truly automate it, no. I would say that not really. Do we provide tools that would allow you to automate it, right? For instance, to expose the JVM metrics through whatever, JMX, for instance, that you can listen to, and then you can change or adjust the container settings. Yes, that part is very easy, and we expose those metrics. We actually expose them in way more details than, for instance, OpenJDK does. An interesting conversation that happened actually just today with a company called Cadify, which is a Kubernetes event-driven autoscaling, and they are working on Keda. And we're actually talking about integrating the JVM to provide the automation to automatically vertically scale the container up and down based on demand. So it is definitely possible. We don't have a ready-made solution, let me call it, as of now, that you would just, with a few clicks or a few lines of code, you would install. What we can offer is much more detailed tooling and observability into what's happening inside the JVM. The screenshots from the screenshots that I showed you from the GC log, the GC poses, they come from a tool named GC Log Analyzer. And one of the differences that we have with Azul Zing JVM is that our GC log contains way more information than the OpenJDK one. The OpenJDK GC log contains only the information about GC activity. What we have there is not only GC activity, but system information, memory information, JIT behavior, the depth of the compile queues, the number of virtual memory addresses, CPU utilization of the process, of the system, memory pages. So what we typically do is that we run the application with our JVM. We get all this detailed information in the GC log. We open it up in the tool, and from there we see very clearly the behavior, the memory behavior, or JIT behavior of the JVM running with your application. And based on that, you can have much more informed decision of what's enough and what is not enough. So, but that's, I want to be honest to you, Ulrich, you know, it's not automated, right? It's not, it's giving you more powerful tools to get the information yourself. Yeah. Hopefully that answers the question. I like Mark's comment, nice GC improvements. I see performance improvements I like. I'm glad for that. That's a reaction that we always like to see. By the way, if you're interested in the kind of log analysis and what other information we provide in the GC logs and how we understand the JVM, feel free to reach out to us, to me. You know, we can definitely do a demo. I don't want to do a live demo right now because that will just go sideways.
I think we have another interesting question. The ready now support that you mentioned, is that based on coordinated restore at checkpoint or CRAC?
Oh, I see. That's a good question. So they are actually separate. So ready now is a technology that has been in the product for quite some time. And what ready now does is that it gives JVM memory, like that it doesn't forget what happened last time. When you run with ready now, you output the decisions that the JIT compiler did. So you produce what we call ready now profile, but it's a glorified name for a text file. And in that text file, you have records of I compiled this method, I compiled that method, these are the dependencies. You know, and then I made a speculation, a JIT speculation for this method. Then this speculation turned out not to be true, so I recompiled the method. So it's a whole log of the JIT compiler decisions. When you restart the JVM, you feed this profile as an input to the JVM, and the compiler is now able to look back what you did with that application. You know, the profile is recorded for a specific application, and it starts doing the compilations proactively, like even without running the method, which is not something that's possible with OpenJDK. So even without running the method, it starts doing the compilations. So in the best case, for instance, and what most of our financial trading customers do is that they try to complete all the compilations before they actually put the traffic in the JVM, and they don't see any spike in latency. Even the first trade of the day is actually very, very fast, which is definitely not possible with OpenJDK currently. I answered about ready now, but the crack is completely different or separate. It addresses the same problem, the warm-up problem or startup of the application, but it takes a different approach. The approach is you actually do a checkpoint, a memory image of the process, and you save that snapshot, and then you restore it. You restore the whole process. The CRAC stands for coordinated restore at checkpoint. The idea behind it is that the memory snapshot cannot be done, or it's not practical. If you do it and then you restore it, the application needs to be stateless, right? Because, for instance, if you have a connection to a DB, right, that connection is no longer active. When you restore the image, what do you do with the connection? Or just simple things like time, right? You take the snapshot yesterday, now you restore it today. What if the application logic depends on time, right? Storage of the time. So that's why we basically signal the JVM, hey, I'm about to take a snapshot of you. Put yourself in a position where you can be snapshotted, close your connection, store the information, etc. And then when you restore it, there's actually a hook again, like, now I'm restoring you, restore the stateful information. Hopefully I answered that question. Yes?
I have a quick follow-up about that myself. It kind of relates to the previous topic. So in Kubernetes, where a lot of us are working, I understand that ready now can easily be shared between many pods. And it's quite easy to set up a health endpoint to make sure the entire ready now is finished, so we can effectively say my pod is only healthy once the warm-up is done.
It's absolutely possible. So the typical combination that we like to do is that we record the ready now profile. We let ready now we then set up a readiness probe, right, in the Kubernetes autoscaler configuration. Let's say, don't give me load in the first 2 minutes, leave some space, right? Ready now does all its things, and after those 2 minutes, the readiness probe succeeds. Or you can do the health check or liveness probe. You can custom made it. You can, for instance, if you're advanced, you can actually custom, you can tailor it to the JVM internal metrics, such as the compilation queues are empty. I'm done with all the compilations, right? And only then I will start taking traffic. That's absolutely possible, and some customers are doing that, right? But that's how we typically use the ready now capability in the Kubernetes world and in auto scaling and kind of auto scaling world, to make sure that your pods and your JVMs and your services start warmed up and not with the sucky performance.
Yeah, I've definitely had use cases for that in finance in the past.
Yeah, absolutely. Yeah. I see another message from Ulrich. How about the metrics you mentioned? Are they available via OpenTelemetry or Datadog? So the simplest thing that you can do is to tap those metrics into Prometheus, for instance, and then ingest it the way you want, right? That's one of the easiest things. The metrics that are provided to, for instance, Datadog, they are controlled by the Datadog agent, Java Datadog agent that you install. We are completely compatible, right, with Datadog. A lot of our customers use the Datadog agent with our JVM, but it only tracks a certain amount of JVM metrics, the ones that are also available to OpenJDK. We have some extra ones that we can expose through special JMX bean that you can, of course, then tap into Prometheus, for instance, or just directly pull through the JMX server or JMX client. So we stick to the basics. When running without any additional JMX beans, you get what you get for OpenJDK. But if you need more detailed metric exposure, you can use additional JMX beans. So another question is ready now and the JDK open source. So we are built on top of OpenJDK, and OpenJDK is GPL v2 license. It is open source by definition. We have, so the core is the OpenJDK core, and anything that's related to it, that's open source. If you ask the sources, you'll get it. You can, of course, for instance, the ready now piece. That is a piece that you can. Sorry, let me rephrase that. You can go to our website. You can click the download button, and you can try out our JVM easily. It's free for testing and evaluation. For running in production, you have to have a contract with Azul, right? But by then we would do a formal kind of POC with you and make sure that you see the benefits that you want to see. And I think that actually answered also the second question: is Azul Zinc free? So for production usage, no. For testing and evaluation, for playing with it, for our developer fund, yes.
Maybe an interesting follow-up on that. I mean, we've discussed that, we get better throughput, we get better um, latency, we get reduced infrastructure costs. Do you have any idea how that balances out with the sync subscription for some of the viewers?
So we always, it always depends. And we always make sure that if you're seeking a cost optimization story, we will make it work so it makes sense, right? If you're going to save $1 million, but it would take, 900,000 for our license, you wouldn't care. So the pricing depends on so many things, on the quantity, on the like how isolated the application is, or multiple applications. Is it a company-wide rollout? It all depends, but it is a basic math. It has to make sense for both parties, right? I see another. Ulrich, you're on fire. So can you describe the different product offerings from Azul, Azul Intelligence Cloud, Azul Platform Core, or Azul Prime? Sure. So I'll start with Azul Platform Prime for two reasons. One is that I'm the product director for that product, and it's my favorite. And the other one is that's what we are actually talking about. So Azul Platform Prime is the name of the product that you buy, and this product has multiple components as part of it. When you buy it, you get to use multiple things. The major one is the Azul Zinc JVM, so the actual JVM, right? But another set of tools in there is a component called Optimizer Hub, which is a kind of separate service that you install, and you can then connect your JVMs to it and do two things. One is to handle the orchestration of the Ready Now profiles. That's a feature called Ready Now Orchestrator, very creative name. And the other one is a Cloud Native Compiler, for short CNC. And the idea is that you don't do the JIT compilations on the client machines anymore, but you actually externalize the JIT compilations to a separate cluster. The benefit of it is that you basically remove any warm-up issues from the client machines, because the JIT compilation is no longer happening there. This is extremely useful in all those scaling use cases where you can't afford the JIT compilation going up and down all the time, but you actually offload it to another service, and then you actually can cache the compilations, reuse them into between multiple instances of the same application, and that's where you can get really cost efficient across the board. We are the first ones that actually brought this into real production. To be fair, IBM OpenJ9 actually had a thing called JIT server in the past, but as far as I know, they never actually took it into production or widely deployed. We have customers that are running hundreds of services using this service as well, externalizing the JIT, scaling up and down without any problems. That's for the CNC, and that's for the Azul Platform Prime. Azul Platform Core is a product that sells support for the build of OpenJDK. So we take the vanilla build of OpenJDK that we call Zulu, Azul Zulu, and you are now provided the support, 24/7 support, some legal guarantees, support for hardware configurations that are no longer supported by other vendors like Oracle, like Java 6, Java 7, some of those legacy things, but also architectures, specific chips that Oracle just doesn't support anymore, and other vendors. So yeah, that's the Azul Platform Core. So it's basically a supported build of OpenJDK. And Azul Intelligence Cloud is a SaaS service, so software as a service, where you can connect your JVMs and then do interesting things with the information that you get from those JVMs. What's that interesting? What are those interesting things? One is code inventory. So that's a feature that allows you to detect unused code within your applications. So it's not like just JetBrains and IntelliJ idea actually, just highlights that it's an unused code. No, that would be too simple. But actually, you can, from the runtime, you can see the runtime information that you're not actually using this code at all. You can detect that from the running JVM. That's a code inventory. Another feature is AVD, Azul Vulnerability Detection. And the idea is that to flag the vulnerabilities, the CVEs that you have running in your code. How does that compare to static scans like Black Duck? Like Black Duck, for instance, is that imagine you have a vulnerable library. Let's take the log4j example from a couple of years ago, which had a critical vulnerability and caused the whole world on fire. Yes, if you can have it as a dependency in your project, and Black Duck will flag it, but if you're not using that code, you're not vulnerable. We are able to have much higher granularity of the information because we are inside the JVM. We see what classes are loaded. We see what classes are used. So it's a SaaS service that communicates with the JVMs. Right now, it does the code inventory, AVD. It does actually a JVM inventory as well, which means information about the JVMs connected to it. So we can quickly see what versions of Java you're using. What is the, do I apply all the security patches? What are the vendors that are connected to it? And that is, for instance, very useful if you don't want to be an Oracle customer anymore because of the pricing changes, for instance. Yeah, that's one of the, that's a brief description. Hopefully I answered that one as well. Okay, well, I think that we're running out of time. Simon, yes. Any last words?
Well, I want to thank you for super useful insights during the questions. It was very interesting. And yeah, I want to thank everyone again for joining and for asking the great questions. And hopefully see you next time.
Thank you very much, everybody. Have a nice rest of the day. Bye.
Have a nice day. Bye.